Recent advances in neural networks have enabled computers to better see and understand the world. They can recognize school buses and zebras and can tell the difference between Maltese terriers and Yorkshire terriers. We now know what it takes to train these neural networks well, but we don't know so much about how they're actually computing their final answers. We developed this interactive deep visualization toolbox to shine light into these black boxes, showing what happens inside of neural nets. In the top left corner, we show the input to the network, which can be a still image or video from a webcam. These black squares in the middle show the activations on a single layer of a network, in this case the popular deep neural network called AlexNet running in Caffe. By interacting with the network, we can see what some of the neurons are doing. For example, on this first layer, a unit in the center responds strongly to light to dark edges. Its neighbor, one neuron over, responds to edges in the opposite direction, dark to light. Using optimization, we can synthetically produce images that light up each neuron on this layer to see what each neuron is looking for. We can scroll through every layer in the network to see what it does, including convolution, pooling, and normalization layers. We can switch back and forth between showing the actual activations and showing images synthesized to produce high activation. By the time we get to the fifth convolutional layer, the features being computed represent abstract concepts. For example, this neuron seems to respond to faces. We can further investigate this neuron by showing a few different types of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to a face and shoulders. We can also plot the images from the training set that activate this neuron the most, as well as pixels from those images most responsible for the high activations, computed via the deconvolution technique. This feature responds to multiple faces in different locations, and by looking at the deconv, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backprop or deconv, we can see that this unit depends most strongly on a couple units in the previous layer conv4, and on about a dozen or so in conv3. Now let's look at another neuron on this layer. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt, and smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting neuron. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool because we never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer, so the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact a book seen on edge, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the DeepViz toolbox and a few of the things we've learned by using it. You can download the toolbox at this URL and explore for yourself. If you'd like to share what you find, you can use the hashtag DeepViz. Thanks for listening, and we look forward to seeing what you discover.
So maybe I should go back here, an important point of this video, the point that is made by Yusinski towards the end, is actually that we have not designed these filters by ourselves. They are learned by data. They are learned by data such that the system as a whole becomes better at classifying the training data. What we have done by choosing the specific convolutional neural network architecture is that we have kind of biased the network towards doing this kind of operation of going from more simple to the more abstract feature extraction. And we have done that by choosing the specific architecture. But the specific thing that this specific filter in the 5th layers is sensitive to faces is an emergent phenomena in the network. So there's been a lot of, this network really made a huge impact and has, as I talked about in the first introductory part of last week's lecture, it has really improved the performance a lot on ImageNet and has been applied in many other contexts. And people have subsequently, of course, improved on the original AlexNet performance, but also other researchers have tried to look into and understand even more what the different filters, what kind of features they pick up. So one work here is from Google. You can go to this URL and then try it out yourself. You can give it an input image, and now you can ask now this input image, you can put that into the network, and it will create filter images in each of the layers. And then you can try to say, now I want to enhance the activation of one of the layers. For example, the output layer, you could say, now I want it to have higher probability for birds. And then you can say, now instead of changing weights, as we learned about last time, we can use the same kind of backpropagation or variant of the backpropagation to change the input image. So that means that if we have an image where there's no birds in it, then it will start to change features that are a little bit like birds, right? So it will then try to put in birds into the image. And here you can see, for example, that we have kind of encouraged it to change Van Gogh's Starry Night into having bird and car features. And then you can see that these start to emerge, the places in the original painting where we have things that could be a little bit like a bird eye or something like that. There's an even more impressive, in my opinion, work that actually dives into the AlexNet, and this is this work from Gattis et al., a neural algorithm of artistic style. And their idea is to say that we can actually, by deriving specific features from the filter images, we can then separate content and style of an image. And you can see the details in the paper. But the point is here now that we can give it an image that we say we want to preserve this content. So this could be this kind of lower image of the houses at the canal, and then we take a different image, and then we say we really want to get the style of that image. So of course Van Gogh's Starry Night is always popular. So we now try to change the original image such that it preserves the content, but we change the style to more like a Van Gogh painting. And we can do that by actually going in different places in the network where we have these kind of simple features to the more abstract features, and then try at all these points to define this kind of style feature and content feature. This is what is illustrated in this figure. So let's look at some examples of where this has been applied to. So we take this image of the canal all the time, and then we try to go and change it into some famous painter's style. So here's, for example, an image by Turner. So you can see the small image on the right hand side with some scenery from the ocean, and you can apply that again to the original image with the houses. You can see it's clearly still the houses, but the style has been changed to this chaotic style chaotic scenery you have in the Turner image. Or you can take Starry Night and you get a really image that which is really in the same style as Van Gogh. And you can take the Scream by Munch, and you can see that you have Scream style features in the image. Or you can take a portrait by Picasso and apply that, and you get something that is really close to that style, or Kandinsky in the last image. And you can see that Kandinsky really can mess up the content here. Here is an implementation of this algorithm by one of our PhD students, and we have taken this image that is an image that is not painted by Picasso, but is shows Picasso, and then we have applied that to a photograph of our president of the university, and you get this nice thing that I really like. And of course this is obvious that this is a way, something that you can use as a present for your mother, so you can give her an image of you can take a photograph of her, and then you can apply a Van Gogh style if that's her favorite artist, and then she will actually get a Van Gogh painting. And this of course also raises the question about copyright of not only of the original painting, but of the style that this painter has painted with. So maybe in the future we actually can copyright our own personal style. Here is a nice movie, so this is like the movie version of Neural Artistic Style that I will play for you now. So it's made by the same group that made this other thing I just talked about. So to the right you can see the image, another Van Gogh image that they have taken the style from. And of course we also need to have a clip from Star Wars. It would not be complete without it. And the next one is nice. I think that's kind of a cave painting meeting Ice Age. And this is probably my favorite. Yeah. So very convincing, and the new thing they've done in this movie compared to the original still image thing is that they have made sure that you get continuity between the different frames, and that makes the image of course much more smooth and nice to look at. Yes, so this was the first part. Now I will turn to the second part of the lecture.